the graph of the equation and finding the rate of change of y with respect to x at that point. All right, guys, we gotta talk about it. This was not supposed to take this long, but you'll get lots of practice over the weekend for doing more of these. So, wait, what? Oh, I missed it. Sweet, yeah, I know. Okay, so the point 9, 1, right? So the point is on the graph, right? So if I look at this graph of the equation, I can identify, about, I pressed things I didn't mean to press. That's okay. So 9, 1 is on the graph. I can't get there exactly right now, but that's okay. But what does that mean? Yeah. Beautiful. Did everybody hear that? Okay, so saying that a point is on the graph means that if we plug in the x-coordinate and the y-coordinate of that point, then it will satisfy the given equation, meaning it makes that equation true. Okay? So what about the point like 9, 1/2? Is that on the graph? No, right? It's like right here. I can't click on it because it's automatically going to go to points on the graph, but it's like right where my arrows are, right? That's not a point on the graph. And we could verify that by plugging in the x-coordinate 9, the y-coordinate 1/2, and seeing that if I plug those values into this equation, that I'm going to get a false statement, right? The left-hand side is going to equal something other than 81, okay? So you have some other number equals 81, which is false, right? Okay. Now, what about this finding the rate of change of y with respect to x at that point, at 9, 1? Okay. So on Wednesday, we talked about how I could, what can I do? I could zoom in on that point and notice what happens to the image when we're looking at the graph. It's no longer looking like some crazy weird curve anymore. It looks a lot like what? A linear function, okay? So this is relevant, okay? So when we find the rate of change of y with respect to x at a given point, without even telling me what the answer is, tell me what it would mean, okay? Let's say we get some number, right? What is the meaning of that number? Interpret slope for me. But what's the meaning of the slope? So it's the rate of change. What is the meaning of rate of change? Okay. So once again, so rate of change, we get it by thinking about changes in y relative to changes in x, right? But what does that mean? So let's say we get like negative, did anybody actually compute? 0.259. Okay, so we will get this answer, okay? What does this number mean? Erin? Uh-huh. Beautiful, okay? So at this, near this point, 9 comma 1, if I change x by a little bit, then the corresponding change, so change x by a little bit, right? Then the corresponding change in y is going to be about negative 0.259 times that change in x. Okay? That's the meaning of the rate of change, right? At that point. Can't forget about this. Now, I said just a minute ago that the fact that this looks linear was significant, right? And so there's this whole conversation that we've been having all semester about approximations versus exact, right? And so one of the beautiful things about calculus is a lot of people call it the study of approximations, right? So, and the study of change. So it's the study of change through the tool of approximations. So what this is often referred to as local linearity, right? And that's because when you look at a small little neighborhood, right, of a given point and you zoom in on the graph, it looks linear, okay? So in particular, if it looks linear, then I can write a linear equation for what the graph, or for what happens between x and y near this point, right? So we were at the point 9, 1. We found that the rate of change near that point is negative 0.259. So what equation could I write to model the relationship between x and y near this point? Keeping that in mind. A linear equation. How do we write a linear equation? So rate of change times change in x. So we're near the 0.91. So change in x would look like x minus 9. So rate of change times change in x is equal to what? A change in y. And near this point, a change in y is going to look like what? Y minus 1. Okay? So what does that mean? That means near this point, if I want to talk about the behavior of the graph, I can just say that it behaves a lot like this linear function. Okay? And in fact, if I were to graph that, if I graph that equation, assuming that that number you guys gave me is correct, then when I graph, so notice I'm graphing, so let me erase it for a second. So it's blue, right? There's the curve. And then when I graph it in purple, you can't even tell the difference, right? Now let me zoom out. Whoops. Okay. And so when we zoom out, right, we can see the blue curve again and see how this purple line like starts to not work so well if we zoom out again, right? Because like at x equals 1, the blue graph and the purple graph completely different, right? But near the 0.91, that's a darn good approximation, right? Okay, and so when you do your homework, this weekend, you're going to be asked to find what they call equations of tangent lines, okay? And this is what's called a tangent line, right? So it is the line that has the rate of change at a given point through that point on the curve, okay? All right. Let me think. Okay, something else that you're going to see on your homework, just as a heads up, is this idea of level curves. So if I were to take this equation and change this number and then graph, now I've got two different graphs on the same set of axes, right? This is what they're talking about when they talk about level curves. So I've got some relationship between x and y, and I can change like the value that I set them equal to, and that will produce different curves. Okay, so just a heads up that that's something you'll see. And then for kicks and giggles, I just wanted to show you something that I think is pretty cool, which is that, so everything that we've been doing, this idea of finding rates of change of y with respect to x when x and y are like intermingled into nasty equations is called implicit differentiation, okay? Because we could imagine y as being a function of x and then finding the rates of change of this entire equation, right? Because when I have an equation relating the quantities x and y, then if I think about the left-hand side and the right-hand side, those are equal, right, when I'm talking about the quantities. So then if I talk about the rate of change of the left-hand side and the rate of change of the right-hand side, they should still be equal, okay? So that's why we take the derivative of both sides of the equation and we can still say they're equal, right? Because the relationship started as equal. So then the rates of change should still be equal. And then we can solve for the rate of change of y with respect to x explicitly, okay? Now, oh, yeah. So we used, so I just want to show you one thing that it can do for us. So we had used the definition of the derivative and graphing calculator to help us decide that the derivative of something of the form b to the x was a constant times b to the x. But some of you were a little dissatisfied because we never actually figured out like explicitly what that constant was. I just gave you a rule and said, oh, that constant is the natural log of b. But we never actually like proved it to ourselves. So I want to show you how implicit differentiation can actually help us prove that that constant is the natural log of b. Okay, so we're going to start with an equation, y equals b to the x. Okay. Now, the problem with this is, like, as it is, right, the only way we could explicitly find a rate of change formula is by having that memorized rule. Okay, so there has to be something I can do to, like, work around that. And so the thing I can do is take the log of both sides. Okay, so if I take the natural log of the left-hand side and the natural log of the right-hand side, they're still equal, right? But now I can apply my rules of logarithms to bring the exponent forward. I'm not taking a derivative, I'm just applying rules of logarithms, right? So I get the natural log of y equals x times the natural log of b. Is that good? Okay, so now notice I have an equation relating the quantities x and y. And I want to find the rate of change of y, right? That was my original goal, was to find the rate of change of b to the x. So that's the rate of change of y, right? So you guys helped me out now. Now I want to find the derivative. So I want to find the rate of change of both sides. So what's the rate of change of the natural log of y with respect to x? One over y times y prime. What's the rate of change of the right-hand side? So what kind of thing is this on the right-hand side? Is it a product of interesting things? This is a constant times x. What's the rate of change of a constant times x? Whoa. It's just the constant. Oh, please tell me you did that yesterday. Okay. It's just the constant. Right? Oh, you got me real nervous about my grading this weekend. Okay? So then if I want to find y prime, then I just solve for y prime, right? So I multiply both sides by y, and I get this. But remember, y was b to the x. So I can plug that back in. And now we have it. Okay? Pretty neat, right? I think it's cool. Okay, so the strategy that I used at the beginning to rewrite using logarithms is called logarithmic differentiation. It's not something that we're going to stress, but just know it's there, and it can be helpful if you have a complicated original function, something where you don't like having the exponent be a variable, for example. Then you can apply logarithms and use the rules of logarithms to rewrite and create simpler differentiation scenarios, if you will. Okay? All right. So moving right along, we've got a little bit of time to motivate the next big idea, which let's just take a look at a scenario. So I've got a 10-foot ladder. It's leaned up flush against a wall, okay, and a monkey comes along and kicks it. Mean monkey. So then it does what you would expect, right? It slides down the wall until it lands on the floor, okay? So what I'd like to do now is talk about how can we mathematize this situation, okay? So this is the scenario that we have, but I want to talk about it, right? I want to talk about things like the rate of change at which the ladder slides down the wall with respect to how it's moving along the ground. Like, I want to talk about it. So what do we need in order to be able to talk about it mathematically? Or the x? Oh, okay. So we need some quantities to talk about, right? So I could call, for instance, what do you want to call it? So you said x is going to be, what did you want to call x? Oh, you don't know anymore. You said something about the floor. Okay. Well, we'll get to rates of change. Before we even get there, I just need some things to talk about. What can I see in this picture? Let me pause it for a second. So if I pause it, what can we talk about? X is going to be what? X is time? Horizontal distance away from the wall. So you want this quantity to be x, right? I like it. So we'll let x be the distance in feet of the bottom of the ladder from the wall. Okay. What other quantities do I have? Yeah, I could talk about this quantity as being the distance of the top of the ladder in feet from the floor. What do you want to call it? That seems very reasonable. Okay. And then this was a 10-foot ladder, right? So then, so I already sort of said, right, I would like to be able to talk about the rate of change of y with respect to x. That's something we've been doing. It seems like I should be able to still do it, right? So if I want to talk about the rate of change of y with respect to x, what do I need before I can even do it? Have we always just had the derivative right away? Where do we have to start? I heard somebody say a function or an equation. What does that function or equation do? It relates the quantities. It's like music to my ears, right? We need a relationship between the quantities involved to start with, right? So can you, looking at this static image for a moment, think of a way to relate the quantities that we've described? The Pythagorean theorem, right? So if you look at this, this is a right triangle, right? And it's always a right triangle, assuming we had really good carpenters who actually made walls go vertically, which I've discovered is not always the case. But that's okay. So we'll pretend that it's an ideal world, okay? And so we can use the Pythagorean theorem. What should this equal? 100, right? Okay. To relate the two quantities, x and y. Now that we have a relationship between those quantities, can I find dy dx? Yes. Help me do it. Okay, 2x plus 2y equals 0. I need a y prime, right? I need dy dx in there. Question? I'm not just throwing it in there willy-nilly, right? It has to be there. Because in theory, y is a function of x, right? It is, somehow I could imagine it being dependent upon x. So then when I look at this y squared, this is a composite function. It's an interesting thing of x raised to a power. So then its rate of change should be 2 times that thing times the rate of change of that thing, right? Okay. All right, so then the rate of change of y with respect to x is? Negative 2x divided by 2y. So negative x over y, okay? Now, so we found a formula. That's nifty. Can we actually make meaning out of it? Okay, so what have we just done? Well, how about this? If I give you an x value of 3, I want you to tell me the corresponding values for y and y prime. And then we can have a conversation about their meanings. Can't tell if the faces are thinking faces or stumped faces. Yes?
Why do you multiply the y in your derivative by dy over dx instead of x? Because isn't x normally affected by the rate of change of y?
Where do you want me to multiply? Wait, what? Say it again.
I'm asking
Here?
why the dy dx is multiplied by y in that instead of x.
So we were finding the rate of change of y squared, which again, we're thinking of y as being some function of x. So if I take the rate of change of a function of x to the second, right, then the chain rule says it's 2 times that function raised to the first. So that's the power rule. But then the chain rule says you have to multiply by the rate of change of that function. So I used this notation, but really the whole time, y is what we've actually got to work with. So this is 2 times the interesting function of x times the rate of change of that interesting function. Did that answer your question? Maybe? We can talk more after class. Or do you have a comment? My original question? Okay. So, so if x is 3, then what is y? Mm-hmm. Yep. Negative. What was it? 3 over the square root of 91. Okay? So let's talk about the meanings of these numbers. Okay? So what does it mean to say that when x is 3, y is the square root of 91? What's actually going on in our picture? Mm-hmm. So 3 is about there. We'll say. Okay. So we've got a distance of 3 between the bottom of the ladder. So 3 feet between the bottom of the ladder and the wall. And square root of 91 feet between the top of the ladder and the floor. And when the ladder is in this position, what's going on? Does anybody have like an approximate, what is this? If you type this into your calculator, what is this? Negative, oh, I did, 0.314. Never mind, I got it. Okay, so what is the meaning of this? Without using the phrase rate of change. What is the meaning? You can throw around the words rate of change as much as you want and not actually tell me anything, right? Because if you don't understand what the phrase rate of change means, you haven't said anything. What does it mean? Uh-huh. No, that's right. So if the ladder slides away from the wall, if the bottom of the ladder slides away from the wall just a little bit, then the top of the ladder will slide negative 0.314 times that much, right? That's the meaning, okay? The fact that it's negative corresponds to the fact that the y quantity is decreasing, right? The ladder, it's not, a lot of people say it's because it's sliding down. Well, no, it's because the quantity y is actually getting smaller, right? In this scenario, that happens to correspond to sliding down, okay? But I don't want you to necessarily attach that as the meaning, okay? It's because the quantity y is getting smaller, okay? Now, if I were to change the setup, right? So that, well, now let me give you, what do I want to give you? Y is going to be 6. Do it again. So what's the corresponding x value? Mental arithmetic? Not so much. I have this really cool alarm clock that makes me do arithmetic in my head in order to wake up. You can't turn it off until you do like a multiplication and division and addition problem. It's fantastic. I highly recommend it. 6 squared is 36. 100 minus 36 is 64. The square root of 64 is 8. Okay. So the rate of change of y with respect to x when x is 8 and y is 6 is negative 8 over 6, which is about negative 1.33. Okay? Now, what does that mean? Give me a meaning. So now we're about here. Yes? Times as much. Yeah. So if the ladder slides away from the wall just a little bit more, then the top of the ladder will slide down the wall 1.33 times as much. Notice when I said that English sentence, I said it'll slide down the wall 1.33 times as much. I didn't say slide down the wall negative 1.33 times as much, because then I'm doing a double negative, which makes positive. We all know, right? So just be careful when you're translating mathematics and English at the same time, okay? Now, if we were to, sorry, it's getting really crowded here, but if we were to concentrate on these changes, right? So this was the change when x was 3, rate of change when x was 3, and y was the square root of 91. This is the rate of change when x is 8 and y is 6. What's happening to the rates of change? Yeah, it's not staying constant, right? So we are not looking at a constant rate of change scenario. Agreed? Okay. Are the rates increasing or decreasing? Negatives are tricky. They're decreasing, right? We're getting more negative. So that's something that we're going to end up talking about. Now, so one thing that I do want to mention is that you want to be careful when you talk about these numbers, not to be talking about, so it's not that the ladder is sliding down the wall faster, right? Because as soon as you say the word faster or slower, you're introducing a time element. And notice we have had this entire conversation without ever mentioning time, okay? So you can't be so flippant with your language, okay? When you talk about this particular scenario that we've described here, there's no time. So all you can say is that the rate of change of y with respect to x is decreasing, right? As x increases. Okay, that's the best that you can say. You can't use words like faster and slower here. Okay, on Monday we will get to scenarios in which we introduce time and continue employing these tools. Okay, so practice over the weekend, and we'll continue our adventure into related rates next week.